All right, let's consider another example. Example 2 says we want to solve this formula, y is equal to ax plus cx for x. Notice x appears here and here. I've got two of them. I'm not quite sure. Let's see if I chose to try to say subtract the cx from both sides. Well, then I have y minus c x is equal to ax. Now I could maybe divide by a, sure, why not? Y minus c times x is divided by a equal to x. Well, that doesn't actually work. That doesn't actually work because I still have x on both sides instead of just one side, and I want it on just one side. So that's not really going to work for me. You may have noticed my helpful hint up top here. Recall our old friend, the distributive property. Distributive property says if I'm given these real numbers, a, b, and c, then I have that a times the quantity b plus c is the same as a times b plus a times c. In other words, I can distribute this multiplication through the parentheses, take a times b plus a times c. Well, if I can do it in the forward direction, I should be able to do it in the backward direction as well. In fact, if we choose to read this backwards, it tells us, oh, that's a terrible look. The contrast there is awful. It tells us if I have a times b plus a times c, well, a appears as a factor, meaning a multiplier, in both terms. A appears in both terms, well, then it can be written out in front. I can pull that out. It's called factoring. You may have studied it in Algebra 1 near the end there. Factor out the a. Let's see what difference that makes in our example. I factor out the x. Notice x is a factor in both terms. It appears as a multiplier in both terms. Means I can apply my distributive property in a sort of backwards kind of way. Pull the x out. If I take the x out of the term ax, I'm just left with a. If I take out of the second term that cx, I'm left with just c. And if I do the multiplication, applying the distributive property forwards, in the forwards direction, I should get back what I started with, and indeed I will. I'll get x times a plus x times c, but we know multiplication has this one little thing where I can write it in any direction, and it's still true. So I will factor the x out of both. Doing that gives me that the formula is now written as we have above. Now I have a multiplication. I have x times this chunk in parentheses, a times c. There's nothing inside that chunk that I care about, so I can just divide it. Just treat it as one whole number there and divide it. I have x times some number. I will simply divide by that number on both sides. Insisting on writing b to c. This gives me y divided by a plus c, and I'm dealing with a fraction here, so these parentheses are implied. I have to treat the numerator and the denominator as if they are wrapped in parentheses. Yes, I noticed that. And what happens? Well, quantity a plus c divided quantity a plus c is just a 1. That gives me x by itself. And if you prefer, write that x equals y over a plus c. That gives it to us. Box my final answer, and we're ready to go. So finally, we got to ask the question, why bother? Because it might just seem like we're just mindlessly shuffling symbols around. And yeah, okay, maybe a little bit. But the whole point here is that we want to be able to take all of these formulas, take our observations, combine them together to form mathematical models so we can answer questions about the world around us. And we are going to be studying multiple models. Throughout this course, you tend to call them applications or story problems. We call them models. Let's see, there's our definition. Our second definition, of course, a mathematical model. It can be a formula or a set of formulas that are developed to represent a real world situation. And what we're going to be studying, so we're going to study, we'll study models that involve the distance, rate, time formula. We're going to be studying models that use different types of functions to answer questions about the world around us. We'll see that the quadratics that you might know and love from Algebra 1 can be used to model certain things. We can use rationals to model work rates and so forth. So we are going to be studying a lot of different models in this class. And the foundation of all of our models are going to be formulas, some from physics, some from geometry, some that we will develop in this class. So that's where we're headed. Look forward to that. All right, so we've seen what a model is defined as. Let's actually look at an example. So here we have a formula given to model the reading difficulty of a text for children in grades 1 through 3 is given as G is equal to 0.0778N plus 4.55S minus 2.2029, where G is the grade level, N is the average number of words in a sentence, and S the average number of syllables per word. So we're given that G is the grade level. G is the grade level. N, average number of words. And S, the average number of syllables per word. So using this formula, we consider the following. Autumn is writing a book for children near the end of 3rd grade. We call it 3.8. So we are told 3.8, that's our G, grade, 3.8. It says that Autumn uses an average of 5 words per sentence. So N is the average number of words in a sentence. So this is our N. Question is, what should the average number of syllables per word be? So what are we being asked for? We're being asked what is the appropriate S in this case. So we could start plugging in numbers. That's an option. Option number 1, we could just plug in the numbers and then go and do our solving. I like to solve in general. So solve first and then plug in the numbers. I tend to make arithmetic errors. If I solve first and then plug in numbers, I tend to make fewer. So if I start with this, that 0.0778N plus 4.55 S minus 2.2029. What I want this is S equals. I want some sort of S equals. I have addition here. So there's an addition here and a subtraction here. So I can undo those. Add 2.2029 to both sides. This gives me G plus 2.2029 is equal 0.0778 N plus 4.55 S. You can take care of this addition here. If there isn't a plus written out in front or a minus written out in front, it is assumed to be a plus. So the opposite of that would be minus, so I subtract 0.0778N from both sides. I now have G plus 2.2029 minus 0.0778 N is equal to 4.5 S. One last thing to do. I have a multiplication right here. I'll undo that by dividing. Now when I divide, I have to divide everything. So I divide this entire side by 4.55 and divide this entire side by 4.55. Recall those implied parentheses. That gives me G plus 2.2029 minus 0.0778 times n, all divided by 4.55 will give us S. Now recall we had G given as 3.8. We had N given as 5. Now we can just plug them in. Plug these in, we get 3.8 plus 2.2029 minus 0.0778 times n, which is 5, all divided by 4.55. And that will be our desired S. At this point, it's a calculator question. Plug and chug into the calculator. So having asked my trusty calculator, it tells me that S is approximately equal to 1.2238. That's 1.2238 syllables per word is what Autumn should go for. I can check this if I want to by taking this value for S back up to my formula, take G to be 3.8 and N to be 5, plug this in and see if it's true. So if I do get indeed 3.8 over here, if I plug in 5 and then that value of S, and you should find that it does indeed work out.